All right, let's start lesson 12.2, rational expressions, page 648 in your book. First thing, let's take an example of a formula here. I equals k over d squared. By the way, this is the formula that tells you the image projection of an image, intensity of that image is equal to the value k, which in this case is how bright your light bulb is, divided by the distance squared. So as your distance gets bigger, your image gets less bright. Okay? All right. What is our lesson about? Our lesson is called rational expressions. Well, what is a rational expression, and why did I show you this formula? A rational expression is any fraction where we have polynomials on the top and bottom. In this case, this is a fraction, and a monomial on the top and a monomial on the bottom, which are monomials are polynomials. Okay? So that's what happens. And when you have that, a rational expression like this, there's always some value of d that or some value in the denominator that if that value turns out to be 0, then this whole problem is undefined. So in this case, if distance is 0, 0 squared is 0, and you can't have a number over 0. So what you say when you're dealing with rational expressions is that if d is equal to 0, then that is an excluded value. In other words, find anything that makes the denominator equal to 0, and that is considered an excluded value. Excluded value. Okay? So once again, a rational expression is any fraction whose denominator and numerator are polynomials, and that when you have that example, when you have that situation, the denominator, if it resolves to 0, you must exclude the value that resolves that to 0. All right, so let's take a quick example of one. Let's take example 1 in your book. What if I had 5m plus 3, polynomial, divided by m minus 6? And in this problem, they're asking you, just tell me what is the excluded values for this rational expression. Well, the excluded values are going to be any value that makes the bottom or the denominator equal to 0. So I can just take that equation that's on the bottom, set it equal to 6 or to 0, and solve it. And I add 6 to both sides, and there is my one and only excluded value to this problem. In other words, if I came up with a value of m, it can't be 6. Because if it is 6, then I get an undefined answer. So the excluded value is 6. Let's look at the second example. The second example, a little bit more complex. X squared minus 5 all over x squared minus 5x plus 6. Now in this example, once again, I want to find the excluded. So I'm going to solve this by saying, well, let's set the bottom value, polynomial, to 0. So x squared minus 5x plus 6 equals 0. Well, I look at that as a quadratic formula, and I know I can factor. So I'm going to factor and set it equal to 0. I know that my first value is always x and x. That gives me my x squared. Now I need to factor, and I'll do it in my head. What two numbers multiplied together give me positive 6, and added together give me negative 5? Well, I can say 2 times 3 is 6, and if they're both negative, they'll add together to be negative 5. So negative 2 and negative 3. Okay? So now I set each of those equal to 0. Because the zero product theorem says that if the whole thing is equal to 0, one of the two, or both, must be equal to 0, excuse me. So I get x equals 2 and x equals equals 3. So my excluded values for this polynomial or this rational expression is 2 and 3. All right, now I'm going to do a little drawing here. What if I have a lever and a fulcrum and a rock, okay? And in this picture, this part of my lever down to the fulcrum is called, it's 5 feet long, or 4 feet, 5 feet. 5 feet long. And this is called the effort arm. And on the other side of the fulcrum, we have 1 foot, and that is called the resistance arm. Okay, so we've got a 5 foot or a 6 foot lever. Total is 6 foot. 5 feet is above the fulcrum. 1 foot is below the fulcrum. We're trying to move this rock. Okay? So the mechanical force formula for that is the length of your effort arm divided by the length of your resistance arm. Well, the length of our effort arm is 5, and our resistance arm is 1. So we have a mechanical advantage of 5. Okay, so in other words, when we use this lever, we get 5 times the power. Okay, and what do we exert? Well, let's say that Kenny, he can put 180 pounds of force down on the lever. So he's going to put 180 pounds down. How much could he lift? Well, the question is, how big a rock could he lift? Well, if he can push 180 and we have a leverage factor of 5, that means that he could lift a 900-pound rock. Okay. Now let's take a look at example 4, or the next example. But before we get into that, I want to talk a little bit about simplifying rational expressions in general. If you remember, if I have AB over AC, I could rewrite that as all the A's together. A over A times B over C. Okay, and if I do that, A over A is really just 1 times B over C, which is B over C. So simplifying from this, I found out anything that I could cancel. A over A can cancel because they're just 1. 1 times anything is just that thing. So what's left over after I find the 1 is B over C. So using that simple example, okay, let's take a look at simplifying a rational expression that's a little more complex. How about this? Negative 7a squared b cubed all over 21a to the 5th b. Okay, well, what I can do in order to simplify this is I can take these two numbers and prime factorize them and then see what's common between them to get the greatest common factor. So the prime factor of this guy is negative 1 times 7 times A times A times B times B times B. So you get my negative 7A squared B cubed all over, well, prime factorization of 21 is 3 times 7 times A, 2, 3, 4, 5, and 1b. So I'm going to now circle anything that's common. 7, and the 7 are common. We have an A and an A. We have another A and another A. We have a B and a B. So if you'll notice that I circled on the top 7a squared b, and I circled on the bottom 7a squared b. So I can say that this problem is really 7a squared b over 7a squared b. That's the things that were common, and they're going to be multiplied times what's left. What's left over here is negative 1 times b, which is negative b squared. And here, what's left is 3aaa, or 3a to the third. And since this and this are really just 1, my final simplified term is negative b squared over 3a to the third. And there it is simplified. Okay? All right. Now let's move on to example number 5. And example number 5 is a little more complex. We have x squared minus 2x minus 15 all over x squared minus x minus 12. So we got two quadratic formulas, and we're trying to simplify that. Well, let's factor both of them. We can say x times x and x times x. We're going to factor them both. X times x. Well, what two numbers on the top multiply to get negative 15 and add together to negative 2? Well, let's see. 5 times 3 is 15, so I want a negative 2, so let's go negative 5 and positive 3. And that gives me negative 2x in the middle and negative 15. And then down here, we have our x and x. What two numbers multiplied together give me negative 12, so it's going to be a positive and a negative. And add up to negative 1. So let's say 4 and 3. And since I want to have negative, I need negative 4, positive 3. Now if I look at it, I've got the same value, x plus 3 on the top and x plus 3 on the bottom. That's really just 1. So I can eliminate those two, and my final answer is x minus 5 all over x minus 4. And there it's simplified. Okay, and then number 6. On number 6, they're asking us what are the excluded values in this rational expression. X squared minus 7x plus 10. Well, excluded values means anything that the bottom number can't come up to be 0. So that's what I'm going to do. I'm going to set the bottom number, x2 minus 7x plus 10, equal to 0. And I'm going to factor. And I'll always have x at the beginning. Now, 2 multiplied together give me positive 10, added together give me negative 7. So I can see right away that's negative 2 and negative 5. Negative 2 times negative 5 gives me positive 10. Add negative 5 and negative 2, I get negative 7. So then I set both of these equal to 0. And x equals 2 and x equals 5. So both of those are excluded values, and let's just make sure they are. Let's check our terms. Let's put 2 into this equation. So we got 3 times 2, we'll put it into the whole equation, minus 15 all over 2 squared minus 7 times 2 plus 10. And if you get that, you get 6 minus 15 all over 4 minus 14 plus 10, which is negative 9 all over 0. Negative 9 all over 0, that's bad. Undefined. Let's check the other one. Let's check 5. We get 3 times 5 minus 15 all over 5 squared minus 7 times 5 plus 10. That gives us 15 minus 15, and that's okay because it's on the top. And on the bottom, we've got 25 minus 35 plus 10, which gives us 0 over 0. Ooh, that's bad. Both undefined. So we see that these two are our excluded values from that problem. And one last thing that's not in your book I want to point out is especially, let's go back and look at example 4 here. On example 4, if I asked you for the simplification, that's what you got for an answer. Okay, I simplified the term negative 7a squared b cubed over 21a5 the b to this by eliminating things. But what if I asked you what were the excluded values? Well, I would look at the simplified term and I'd say just as long as a isn't equal to 0, I'm fine because it's being multiplied here. But before you look for excluded values, you got to look at your original problem because the original problem may require a different variable on the bottom, and this one does. It actually requires a b. So the excluded value of this, a cannot be equal to 0, and b cannot be equal to 0. So those are your excluded values right there. Okay? Notice that the difference. When you're talking about excluded values, figure it out from your original equation. When you're talking about non-excluded or simplifying, then you should have already done your excluded values.